Okay, here we are again. Now, as usual, I need to check my audio. That's fine. And let's see here, sharing screen. And as usual, I have to clean up my desktop clutter. And we're in business. Okay, so here we are with example 5. Okay, as usual, where are you and what do you got? We are in 3 dimensions, right? Our vector field has 3 components. That's so the giveaway there. Also a giveaway is that we've been asked to compute a flux, and there is no such thing in, well, there is no surface flux in 2 dimensions. No such thing as a surface integral in 2 dimensions. Okay, so on our diagram, again, I got to clean up from last time here. We are in R3, looking at the R3 diagram. And again, you know, look, don't forget there's an R2 diagram up here. And for the appropriate questions, you got to look at the R2 diagram. These are in R3. So we're there. We've been asked to compute a flux. There's our fluxes. And when you've been asked to compute a flux, that vector field you've been given, the diagram, come here. The diagram suggests I should compute the divergence of that vector field. So let's do it. Let's compute the divergence here. And divergence of F is, okay, the X partial of that, which is Z, plus the Y partial of that, which is minus Z, plus the Z partial of that, which is 0, which adds up to 0. So my divergence is 0. Let me show you the landmine. Here's what a lot of students do wrong. This is such a tragedy. I hate to see this. Oh man, it's so tragic. And I see the lure, right? I see the pull to do the following. You see that the divergence is 0, and you've been asked to compute a flux. And so many students will say, "Oh, a flux." Well, fluxes are triple integrals of divergence. And we just computed the divergence was 0. And so therefore I get 0. And a lot of students will write this down and, you know, call it. This doesn't work. It really, really doesn't work. This is maybe 3 points out of 20 because nothing in that argument is valid. Going over to the diagram, sometimes fluxes are triple integrals. But remember, these theorems come with conditions. There's conditions on using the divergence theorem. To use the divergence theorem, your surface has to be a boundary of a region. There has to be a solid whose boundary is your surface. You have to have an anti-boundary surface, however you want to see it. Is that the case here? Well, for one thing, it's not. For another thing, the student did not address it, right? This hypothetical, argument here where the student writes, that. So, in fact, this surface, though, is not a boundary. We can, let's give an exploration of that real quick here. And I guess I'm going to clean up this. Okay, let's think about our surface. Our surface is, well, there's an upside down paraboloid. We're looking specifically at the part of that paraboloid where Z is positive. So our surface is actually, let's see here, I'll do like this. Our surface is this right here. Okay. And that's not a boundary. That's an upside down bowl, right? And it's just, it's not a boundary of anything. It does not enclose any volume. It doesn't enclose anything at all. So any assertion then about using the divergence, no, there is no divergence theorem to use. It's not that the divergence theorem is false, it's that divergence theorem doesn't apply. And so everything that a student would write down, as soon as they write down this, they're in garbage land. Nothing is valid, nothing makes any sense, nothing has anything relevant to do with the problem or an actual solution to the problem. Very bad. Okay, I make a big deal out of this, and I think I made a big deal out of this in class yesterday as well, because it's a very common landmine to step on, because there is that pull. You see the divergence is 0, and you imagine how great wouldn't it be if I could just put a 0 there, and you see daylight at the end of the tunnel, and you run for it. Anyway, be careful. Be careful not to make that mistake. While I'm here, I also want to talk about correctly interpreting what the question says. Notice what I have a drawing of here is my surface S. Sometimes the way students draw things misleads the students into thinking about, into misunderstanding what the surface actually is. Sometimes the drawing actually can be deceptive. So you might have thought it was weird that when I drew this upside down paraboloid, I didn't sort of do this. I didn't draw and there's the sort of the edge. Normally we draw edges. If you do that, you have to make a very conscious note in your mind that what you've drawn there is the boundary. It's not a corner. It's a boundary. This is where our paraboloid gets sliced off. From all the bit at the bottom, it gets sliced off by this plane here, cuts through it, and everything below that just kind of falls off. Okay, leaving this surface open. This is still open at the bottom. But when you draw this, a lot of students' imaginations then will kind of fill in and say, oh, well, then, but don't we also have that? Isn't that part of my surface? No, not at all, and not in any sense. And there's nothing about what's written up here that suggests it. And you gotta make sure to interpret the question as it's written. This very clearly says that we're looking for points for which that is true. Here, let me go back to the correct colors here. I need this to be true, which means I've got to be on the paraboloid. And I need for this to be true, which means that I need to be above the XY plane, right? So the points that satisfy all those rules are the ones that I have drawn here. These points that I have in red, they don't satisfy that rule. They are not on the paraboloid. They're not part of this surface. Okay. So again, be really careful. Make sure to interpret the question carefully. Look carefully, fine tooth comb, think about every little bit. Don't, read the question fast and loose and then answer some question that you're 70% confident was the right question, right? Because then you've answered the wrong question, and the tools used are just not the same, and it's not what we're interested in. Even worse, this kind of dovetails with my previous warning. In this case, if you misunderstand what the solid is or what the surface is, if you mistakenly have that in there, I better put it. Okay, so of course, wrong, right? If you mistakenly have that bottom thing in there, then all of a sudden your misinterpreted surface is a boundary of a solid, and that would lead you to write down Gauss's divergence theorem and think that you have a right answer, and it's just as wrong as the previous complaints that I made about such a thing. It's equally not an answer to the question at hand, and it just doesn't work. It doesn't make any sense, and the fact that it's the correct answer to a different question is just not relevant. Super dangerous. Be careful to interpret the question correctly, and be careful that if you're going to use something like the divergence theorem, make sure that you confirm that you're looking at an actual boundary surface. Because if you're not, then it's all nonsense. Okay, enough of that. Enough of the warnings. Okay, so back to the actual question here, and we have this surface, and divergence is 0. What do we do with divergence being 0? We definitely don't use the divergence theorem, right? This is not a closed surface. So what do we do? And come back over here to the diagram. And, I don't have this drawn on the diagram, but make sure to recall that a vector field whose divergence is 0 is also a vector field that has an anti-curl. Hey, maybe I could use Stokes's curl theorem. Problem, I don't know how to find anti-curls. Right, so that doesn't really, I mean, so that, kind of, but ultimately not really, because we don't know how to find these anti-curl vector fields that we would need if we were going to use Stokes's theorem. So that's not really an option either. But there is this third equivalent form. Don't forget these special fields. Divergence is 0. Have an anti-curl. They're also surface independent. So you're going to get the same value for the flux with any other surface that has the same boundary curve. And that's going to be the really useful trick in this case. So now we got to think through, what is our boundary? And now, of course, our boundary is, whoops, I wanted to be in purple here. Our boundary is this. We got to think about orientations. We did one of these in class yesterday. So let me use the same sort of argument that oriented upward. And if it's oriented upward, that means in this case anyway, it's like that. And so, you got to do this yourself with your own right hand because perspective is going to be different. This being on camera, you're effectively looking at me backwards here. But thumb in the direction of the normal vector. Look at the way that on your right hand that your fingers swirl, and they swirl kind of like that, right? And then think about how that relates down here. How does that sideswipe against the boundary down here? And it sideswipes again. Color choices. I'll use red. It's fine. It sideswipes that way. Okay. All right. So there's our boundary. There's the boundary that we have to preserve. And with that in mind, I can pick any other surface that has that boundary. Of course, you have a lot of options. And if you wanted to be silly, you could, use a surface like that. Why would anyone do such a thing? I can't imagine. But vast majority of the cases, if it's an option, not that it always is, but if it's an option to use a flat, so if your boundary curve is entirely within a plane, and thus you have the option to pick, the enclosed portion of that plane, usually that's your move. That's your best choice. Now, again, you got to think about the orientations on that new surface, right? So we've jettisoned I'll keep my colors straight. We've jettisoned that surface. I'm not going to use it. Now we're using this green surface. And how is it oriented? Well, you got to play the game. Okay, so hypothetically, if it were downward, down, thumb, fingers, swirl, side swipes, and that would sideswipe the wrong direction. So not that. And so what about this one? Thumb, fingers, swirl, side swipes. And that does side swipe correctly. So our new surface oriented upward. Here we go. Oh, let me just do it like this. Okay, so there's our new surface oriented upward. And you can compute the flux through that new surface. So let's do that. We've executed our surface independence. Again, we've long since jettisoned that surface. Its only role, as far as we're concerned in this question, really, is to help us understand what the boundary is that has to be preserved as we create the new surface that, of course, we're going to work with instead of that ugly thing. Okay. Okay, so yes, you gotta love path independence. Excuse me, surface independence. Surface independence. Really, really nice trick. It's so convenient to be able to just change to any surface we want. These are lovely vector fields that have this property. Okay. Yeah, so let's write it down. Now we've got a flux integral to compute here. Flux now over our new surface. I'm going to call my new surface S2. I have F dot ds. Oops. Which, of course, you can write down several different ways. And if you want to parameterize, you could. But in this case, look what happens. If I instead play this move, I'm rewriting the ds vector as little n ds scalar, because I can write down that little n vector very easily. I know I can see exactly where it is. There it is. It's 0, 0, 1. It's part of a flat, perpendicular to a part of a flat plane and pointing upward. It has to be 0, 0, 1. So when we write it all down together, then that normal vector being 0, 0, 1, our original vector field being where there's so many colors, xz minus yz 0. This just turns into 0, which is pretty sweet. Okay, so Stokes, excuse me, surface independence here was a huge win. Huge win. All right, now that said, I am going to show you how to use Stokes's theorem, which is why I misspoke there. I was thinking ahead. How to use Stokes's theorem to solve this problem. It's arguably just as good. I don't know, by ballpark just as good. Let's see that in action. I'm going to, whoops, I'm going to slide all this out of my way here. Put that down there. Let's remind ourselves of our picture. We have our surface is like that. It's got a boundary that is, about like that. I'm just going to go ahead and solidify that. There's our boundary. Stokes's theorem. In order to apply Stokes's theorem, let's go back to here, remind ourselves what we're doing. We gave ourselves a maybe on that because we don't know how to find the anti-curl, right? Here, let me clean up the mess here. We'll do this over again. We took our vector field, we took the divergence, we got 0, thus allowing us to conclude that yes, there is an anti-curl. And then we abandoned this line of reasoning almost immediately because we don't know how to find the anti-curl. Or do we? In this case, it is explicitly given right here in the statement of the question that our vector field F, here, let me do it like this. Our vector field F, this thing whose flux we want to compute, we are explicitly told that that is the curl of an explicitly given field here. I didn't even give a name to it. I guess I'm going to give, let's call it G. It is the curl of G. So my anti-curl is given. So, you know what? We can use Stokes' theorem after all, as it turns out. Stokes' theorem, again, the anti-curl is given. It's G in this case. So, you know, this diagram is generic, of course. But a line integral around the boundary of the anti-curl field will compute the original flux for us. So, okay, back to here, we're going to be looking at then a line integral. Line integral around this boundary curve, boundary of S, of our anti-curl dot dx. Okay, now we have this integral to think about. How do we go about computing this integral? So is this going to be easier? Kind of seems like I'm going to have to parameterize this curve. Not that that would be the worst thing in the world, but it is going to be sines and cosines. At least it seems like it will be. And then you notice, yeah, but that's a nice curve. Notice that curve is entirely contained within the XY plane. And being entirely contained within the XY plane, that means Z is not changing. Z is constant. Z is always 0. And that actually tells you a couple of really great things. For one thing, with Z not changing, my dx vector, I can rewrite as, dx dy, and it's tempting to say dz, but z isn't changing. So dz is 0. And the other observation that you can make is that, well, as I just said, on our curve, z is 0, and that makes that 0. Right? So for more reasons than we need, this dot product is 0, and therefore that integral is 0. So, you know, take your pick. Do you like this Stokes' theorem, you know, anti-curl approach? Again, capitalizing on the fact that the anti-curl happened to be given. It wasn't immediately, I didn't use the word anti-curl is, right? But it's implicit in the algebra that's written here that I am telling you the anti-curl, right? Or if you like the surface independence argument, that's also really crisp. It's really efficient, and another fine way to do it. That surface independence approach down here, yeah, also just fine. And I don't know which one I like better, to be honest. They're both really good. Okay. All right. Last example. Again, in 3 dimensions. Again, we're computing a flux. Whoops. So going back to our diagram, again in 3 dimensions, again, we're computing a flux. So again, whatever our vector field is, we're going to compute the divergence just because it says so and because it's likely to be useful. We compute the divergence of this vector field, and let's see, divergence of F is X partial of that, which is 1, plus the Y partial of that, which is 1, plus the Z partial of that, which is -1, which adds up to 1, which is not 0. And that tells me right away, did not get 0. That means don't even think about trying to find an anti-curl using Stokes' theorem, nothing of the sort. That's not going to work. Right? There is no anti-curl. So waste of time. Okay, so let me just put a big red X through this. We won't entertain that anymore. Oh, also, no surface independence. Forget about surface independence, right? So you're stuck with the surface you got. Okay. Okay, now, but let's think about our the other possibility. You know, maybe we can possibly use this theorem. Maybe we don't have to brute force this. Can I use the divergence theorem? Well, I would need to know if there's an anti-boundary region. Does my surface enclose a region? And yeah, again, you can think about that a couple of different ways. If the opportunity happens to be convenient to entertain whether the surface whether its boundary curve is, exists or doesn't exist. You could take that approach. But in this case, it's easier just to look at the sphere, look at the surface. Our surface is the sphere. And we have an orientation issue, but the sphere, it encloses a solid. There is this solid on the inside there. So this is looking good, actually. There is an anti-boundary region. I am going to have to play with orientations, but it's looking like using the divergence theorem here is the move. Okay, so for which, by the way, we've already computed the divergence. So lucky break. Again, not lucky particularly, but that's one of the reasons we compute the divergence is it's liable to be useful in different ways. Okay. So, our sphere, of course, is oriented inward. That's not how boundaries work. And so I need to say, S minus is equal to the boundary of the ball. And I really should label what I mean by the ball here. The ball radius 1 centered at the origin. Unit ball, I guess I could say even. That would have been easier. And then we proceed to compute as follows. We say the integral over S, well, that's the negative of the integral over S minus, which that minus sign, of course, comes along for the ride. The integral over S minus is the triple integral over the ball of the divergence. Right, and we've turned our flux question into a triple integral problem. Oh, and of course we computed the divergence already. The divergence was 1. So I have a negative triple integral over the ball of 1 dV. And of course, now this is an easy geometry problem, right? We know the volume of the ball, and easy integral, and the flux we're interested in is the negative of that. Again, don't forget that this minus sign carries through from the original minus, which arguably really is kind of that, because the point is the boundary is oriented negatively. It's oriented opposite of the surface that we're actually getting. So there you go. That one works out pretty nicely. Okay, all right, those are my 6 examples. I hope these were helpful. There's a lot of tips and tricks and weird circumstances and landmines and things to worry about involved in these kinds of questions. And I hope this little tour of the area is going to help you to get good at computing these kinds of things. All right, see y'all in class.